Hi there, this is Capacitance Lesson 4, Discharging a Capacitor. So we need to know the charging graphs. So a couple of lessons ago, I believe it was lesson 1, we went through how a capacitor actually charges. So the graphs, I'm going to draw them one at a time so you can write these down. So let's do current. So if you had current against time. So current always starts off high and finishes low, and it discharges something like this. Okay, so that's current time graph. So it might be a charging graph, but current starts high. If you remember the analogy of the empty bus or the empty cinema, current flow starts high, goes down low. It's the opposite too. So let's have a look at a voltage graph. So voltage against time. So if you're charging a circuit, so obviously voltage starts off low and it charges like this. Then we've got one more. Remember to pause at any moment if you wish. Then we've got one more. Let's do charge against time. So charge again, if you're charging, starts at 0 and goes up like this. Hopefully that's okay. Just if you get those down, then we'll do the discharging graph, sorry. So on a discharging graph, the current again starts off high and decreases over time. The current graph always has the same shape in both scenarios. Current flow, when you've got a fully charged capacitor, the current flow initially will be very high and diminish. And then we'll do the other graphs. So we've got voltage against time. So if we're discharging, the voltage initially will be high and it will decrease over time. Looks something like this. And then we got one more, the charge graph. So charge against time. So charge initially will be high and then we'll discharge it and it will come down like that in the same manner as the voltage graph. So hopefully you've got them in your book, hopefully neater than the ones that I did as well. Let's move on. So capacitor discharge. So here's a little circuit. So you've got a capacitor with a resistor and a power supply. So capacitor C is discharged through a resistor R. So what will happen is we will flip the switch this way and close that circuit up and charge the capacitor. Then flip the switch the opposite direction and discharge it through that resistor. Obviously the resistor will give off thermal energy to get rid of the energy in the capacitor. So the charge Q left on a capacitor initially, charge Q0 after time t, is given by Q equals Q0 e to the power minus t over RC. Because charge is proportional to voltage through the Q equals VC, we've also got V equals V0 e minus t over RC. And also, because voltage is proportional to current, we can also say that the current is equal to the maximum current E minus T over RC. So Q is charge, Q0 is maximum charge, E is the anti-log, the anti-natural log. So to get the E on your calculator, you would probably have to press Shift LN. So log shift, and that will give you the anti-log, the number E. T will be time, R is resistance, C is the capacitance. So the V's are the voltages, and the I is the current. So the time constant RC. So it's the time taken for the capacitor to discharge to 0.37 times of its initial charge, or its initial voltage. So the time taken for the discharge current and potential difference, it's 4 to 0.37 of their initial values. If you want to make some notes on that, please do. Just pause the video. And the time constant, which we call tau, is indeed equal to RC. So that's the equation. So the time constant tau is measured in seconds, R is resistance in ohms, C is capacitance in farads. Let's move on then. So why is it 0.37? Why is the time constant the amount of time it takes for the voltage or the charge to drop to 0.37 times its initial value? Well, I'm going to show you now. So let's get our equation. So the equation, Q, the charge is equal to the maximum charge, E to the minus T over RC. So that's the equation. So it drops to 0.37 after a time that is equal to the time constant. So the time T there, I'm going to make that equal to the time constant, RC. So we can write this as Q equals Q0 E to the power of, and it's just going to be RC divided by RC. And so minus RC over RC is minus 1. So whatever the number Q0 is, if you multiply it by E to the power of minus 1, which you can do on your calculator, so shift ln natural log minus 1 equals, will give you 0.37. So after one time constant, the proportion remaining will be 37% of its original value. And you can practice that for different ones. So you could do 2 time constants, so you could try e to the minus 2. You could do 3 time constants, which would be e to the minus 3, and so on. And we've got a question later where we utilise this as well. So hopefully that's okay. Let's move on from that. So if you want to do this question, please pause. Calculate the time constant for a capacitor of 1500 microfarads and a resistance of 2 kilo ohms. So the time constant tau is equal to RC. So the resistance is 2 kilo ohms, so 2 times 10 to the 3. Multiplied by 1500 times 10 to the minus 6 farads. And if you calculate that, that will give you a time constant tau of 3 seconds. Let's move on to the next one. If you want to pause and have a go at this. So a capacitor of 5000 microfarads discharged by a 12 volt supply and then discharged through a 150 ohm resistor. So the first thing we're going to do is calculate the initial charge. So that's the equation that we did in previous lessons. Q equals VC or CV. So it's 12 multiplied by 5000 times 10 to the minus 6. And that gives us an initial charge of 0.06 coulombs. Then let's do the time constant. So the time constant, quite simply, is RC. So resistance 150 multiplied by the capacitance 5000 times 10 to the minus 6. So that gives a time constant this time of 0.75 seconds. And then let's do part C. So the charge remaining after 1.5 seconds. So we're going to need this equation. So the charge is equal to maximum charge E minus T over RC. And then let's put some numbers in. So the charge is equal to the final charge, or the maximum charge, 0.06, multiplied by the number E to the minus. So the time is 1.5 seconds, divided by the time constant, which we calculated a second ago, is 0.75. So you can put that into your calculator in one go, and that will give you a charge that is equal to 8.1 millicoulombs. Hopefully that's okay. Let's move on to the next bit. So let's pause and have a go at this video. This question, sorry. It might take you a while, there's quite a bit to it, and then I'll take you through parts A to E. So let's go for it. So A, we're going to calculate the initial charge on the capacitor. So charge is VC, so Q equals VC. So we've got 24 volts and multiplied by a capacitance of 4 microfarads, 4 times 10 to the minus 6. And that gives us a charge of 96 times 10 to the minus 6 coulombs, or 96 microcoulombs. Okay, let's do part B. So the initial current through the 200 ohm resistor. So we can just use Ohm's law, V equals IR. So the current is voltage divided by resistance. So we've got 24 volts divided by 200 ohms. And 24 divided by 200 gives us 0.12 amps. Pretty straightforward. Time constant also straightforward. So the time constant tau is equal to RC. So we got the resistance, which is 200, multiplied by the capacitance of 4 microfarads, 4 times 10 to the minus 6. That gives a time constant of 8 times 10 to the minus 4 seconds, or 0.8 milliseconds, which we'll use momentarily. So part D, the charge on the capacitor after 4 milliseconds. So remember the time constant, I'm just going to jot this up here, that we just got was 0.8 milliseconds. So charge after 4 milliseconds, so it'll be Q equals, so we've got Q naught, E to the minus T over RC, RC being the time constant. So the charge is equal to the maximum charge, which we calculated earlier, which was 96 microcoulombs. So 96 times 10 to the minus 6, multiplied by E to the power of, and the time is 4 milliseconds. So we've got minus 4 divided by the time constant 0.8, and 4 divided by 0.8 is obviously minus 5. And then just put that into a calculator, so it's 96 times 10 to the minus 6 multiplied by E to the minus 5, which gives us, let's calculate this, 0.647 microcoulombs. Or 6.5 to the minus 7 coulombs, however you've written it. Then we just got E to do. So E, find the current through the 200 ohm resistor at T equals 4 milliseconds. So because charge is proportional to current, Q equals IT, we're going to use current is equal to maximum current, E to the minus T over the time constant. So let's just put our numbers in. So the maximum current, which we got initially, was 0.12 multiplied by E to the power of minus 4 milliseconds divided by the time constant of 0.8 milliseconds. So it's 0.12 times E to the minus 5, which gives a current of 0.81 milliamps. So quite a tough question. Hopefully that went okay. Let's do one more, final question. So after 5 time constants in any capacitor and resistor combination, is the amount of charge remaining less than 1%? So you've got to show that mathematically. So you've got to pause that and do it. So let's have a look. So I touched on this earlier. So Q is equal to Q naught, E minus T over RC. So 5 time constants for the amount of time would give a time equal to 5 times the time constant, 5 RC. So we can write Q equals Q naught, E to the minus, the time is 5 RC, divided by RC. So E to the minus 5. So if we do E to the minus 5 on our calculators and times it by 100, that will give us the percentage remaining after 5 time constants for any charge and resistor combination. So E to the minus 5 times 100 is 0.67%. So after 5 time constants in any capacitor and resistor combination, is the amount of charge remaining less than 1%? Yes, it is. It's 0.67. Hopefully that went okay. Thanks for watching, and I'll speak to you soon.